A steel erector slips from a 20-foot I-beam. Gravity takes hold and he plummets toward the concrete deck. Then a violent snap. He stops, suspended exactly 18 inches above the slab. Surviving a drop like this has nothing to do with luck. It is not the result of wearing thick nylon straps or a heavy-duty harness. That 18-inch margin of survival is dictated by a rigid, unforgiving architecture of mathematical engineering and physics. The fundamental physical reality of a fall begins the moment a worker loses contact with the beam. Gravity accelerates the human body at exactly 32.2 feet per second squared. After just 6 feet of freefall, a standard 200-pound worker reaches a velocity of roughly 19.6 feet per second. In that brief window, the body generates a massive amount of kinetic energy. That kinetic energy cannot simply vanish. To stop the fall, the energy must be forcefully dissipated. The equipment itself has to perform physical work on the body to absorb the load. A personal fall arrest system is an active kinetic energy management system. If the mathematics governing that system are wrong, the gear designed to save a worker instead becomes a lethal weapon. Consider a theoretical scenario where our 200-pound worker falls 6 feet, but is caught by a rigid steel cable with zero stretch. Stopping instantly compresses kinetic energy into a fraction of a second, producing forces exceeding 30,000 pounds. This shockwave destroys internal organs and snaps the spine, then travels straight up to the anchor point, shearing bolts directly out of the concrete. The only way to solve this physical crisis is through the work-energy theorem. The work-energy theorem is a physics principle stating that the work done to stop an object equals force multiplied by distance. Because the total work required to stop the falling mass is fixed by gravity, there is a strict mathematical relationship. To decrease the lethal impact force, you must artificially increase the deceleration distance. Surviving a fall requires elongating the arrest over time and distance. Without that elongation, the resulting forces will far exceed human biological tolerances. The Occupational Safety and Health Administration, or OSHA, sets a legal threshold for human survivability. They mandate that a personal fall arrest system must limit the maximum arresting force on a worker wearing a full-body harness to 1,800 pounds. But OSHA Regulation 1926.502 legally mandates that the anchor point supporting that system must hold at least 5,000 pounds per attached worker. A dangerous assumption persists on job sites that this 5,000-pound rule is a static weight requirement, as if workers are regularly suspending pickup trucks from the ceiling. The true engineering purpose of the 5,000-pound mandate is to establish a dynamic safety factor. It is engineered to be roughly 2.78 times the 1,800-pound biological force limit. This chart maps force over time during a fall arrest. The 5,000-pound capacity line exists to absorb the violent, unpredictable loading surges that ripple through the system the moment a worker suddenly drops. This is why a properly engineered structural anchor is vastly different from a field improvised tie-off, like a guardrail post or a piece of electrical conduit. An improvised structure might feel strong when you push against it with static weight, but it will instantly shear or buckle when subjected to thousands of pounds of dynamic loading in a fraction of a second. The 5,000-pound rule has nothing to do with the static weight of the worker. It exists entirely to contain the explosive kinetic force generated by gravity. With a 5,000-pound anchor secured, the focus shifts to the connecting device between the worker's harness and that anchor. How do we artificially create deceleration distance in midair? One solution is the energy-absorbing lanyard, which houses an internal, accordion-folded section of webbing. This inner section contains partially oriented yarn, or tearaway webbing, specifically designed to rip apart under extreme tension. This controlled destruction dissipates the kinetic energy over time. By legally restricting the deceleration distance to a maximum of 3.5 feet, the lanyard continuously bleeds off force as it tears. That 3.5-foot physical expansion is the exact mechanism that caps the maximum force exerted on the worker below the 1,800-pound limit. Because these lanyards rely on their own physical destruction to work, they are strictly single-use safety devices. Once they are deployed, they are permanently compromised. This destructive mechanism contrasts sharply with the mechanical approach of a self-retracting lifeline, or SRL. Inside an SRL is a centrifugal braking system. As the cable accelerates during a fall, high-speed metallic pawls snap outward, locking into gear teeth to halt the line payout in mere inches. Whether through the violent ripping of folded webbing or the immediate locking of steel gears, these devices exist solely to manipulate physics and prevent kinetic forces from destroying the human body. There is an ultimate paradox in fall protection. A worker wearing a compliant harness attached to a perfect 5,000-pound anchor can still be killed if the environmental geometry is ignored. This brings us to total fall distance. Total fall distance is a non-negotiable mathematical equation that dictates exactly how much empty vertical space is required below a worker to safely arrest a fall. Looking at this chart, we build clearance downward. First, a 6-foot lanyard freefall. Next, a 3.5-foot deceleration distance. Then, worker height and harness stretch add 6 feet. Finally, a 2-foot safety factor. This requires 17.5 feet of total clearance. These numbers cannot be compressed, and they cannot be ignored. They are strictly dictated by the physical length of the deployed materials. Tying off at foot level with a standard 6-foot lanyard mathematically requires almost 18 feet of unobstructed airspace below the anchor point. If the lower level is less than 17.5 feet away, the fall protection system will not have the physical space required to fully deploy, guaranteeing a severe impact with the ground. When we apply this math to a real-world construction site, the severity of the hazard becomes obvious. The space below a working deck is rarely empty. It is filled with concrete decking, with exposed rebar, and lower scaffolding. Working at 15 feet while tied off to the floor with a 6-foot lanyard is a mathematical guarantee of catastrophic injury. When clearance is tight, the geometry requires strict operational solutions. You must move the anchor point overhead to eliminate the freefall distance entirely, or switch to a self-retracting lifeline to severely restrict the deceleration distance. Safety equipment cannot think for the user. Once gravity takes over, the gear will blindly follow the laws of physics. A competent safety professional must calculate the exact geometry of the deceleration before a worker ever steps near an edge. Simply putting on a harness does not save a life. Mastering the physics and mathematics of the fall before